Chidanand Kumar will be presenting paper ID 14 titled Multi-Scale Voxel Class Balanced ASPP for LIDAR Pointcloud Semantic Segmentation. Author includes myself Chidanand and my colleague Dr. Samir Al-Stouhi. What is semantic segmentation? Each and every point in a point cloud will be assigned one of the class labels. We trained our model on semantic kitty training dataset, and the resulting video sequence that we are seeing as of now is the result of one of the sequence on testing dataset. In semantic kitty, there are 19 classes and are evaluated on semantic kitty leaderboard. Also, in the video sequence, we can see segmentation results on classes like road, parking area, car or vegetation or sidewalk or walls, yielding meaningful results. We obtain the semantic segmentation by converting 3D point cloud to 2D polar bird eye view representation. Recent approaches to semantic segmentation exploit data from different sources like camera or LIDAR. Camera-based approaches have drawbacks like limited field of view, difficult to work under low contrast conditions, and inability to determine precise distance within the surrounding outdoor environment. On the other hand, LIDAR sensor is used to create 360-degree view point cloud, solving limited field of view problem in cameras. LIDAR data is more robust to changes in weather and illumination issues in indoor or outdoor environment. Point cloud is close to realistic data in the world. They capture 3D shapes much better than camera and the representation is very much simple. However, we face enormous challenges in LIDAR. Raw point clouds are typically irregular, unstructured and unordered. Although well-known deep CNN networks performs better on structured 2D computer vision tasks, they cannot be directly applied on unstructured point cloud data. Even though state-of-art results of PointNet can be extended, but they are limited to 3D point cloud in smaller number, but not for large-scale point clouds which contains millions of points. Point cloud data is very noisy, partial and completely sparse. The classification results of LIDAR data should be invariant under geometric transformations. Coming to the background, we had three different types of approaches. In point-wise methods, we directly process the raw irregular 3D points without applying any additional transformation or pre-processing. Even though these methods are powerful on smaller point clouds, their processing capacity and memory requirement unfortunately becomes inefficient when it comes to 360-degree LIDAR scans. In projection-based approach, they convert point cloud to 2D pseudo bird eye view representation to make use of 2D CNN to achieve state-of-art results. In 3D voxel partition technique, they convert a point cloud to 3D voxels and apply 3D convolution on these voxels to produce LIDAR semantic segmentation. The name MSB, CB, ASPP comes from the following below facts. Here we present a unified hierarchical way to construct meaningful features from the point clouds to improve semantic segmentation accuracy by designing bottom-up voxel feature aggregation from multiple scales and top-down pathway of pyramid-like structure. To improve accuracy, class-balanced weighted cross-entropy loss is used in conjunction with Lowell's softmax locks. To boost the performance, we enhance the features of the encoder using ASPP or dense ASPP to enlarge receptive fields and dense interconnection feature maps. Improves training time of PolarNet by incorporating learning rate scheduler in addition to existing ADAM optimizer for faster convergence only with fewer epochs without compromising on accuracy. We achieve state-of-art result both in terms of speed and accuracy. Our high-resolution grid model is able to get 60.6 MIOO at 21 FPS, whereas our low-resolution grid model achieves 54 MIOO at 38 FPS, thereby balancing between accuracy and speed trade-off. Following is the below hierarchy of our architecture explanation. Method. Given a set of n LIDAR point clouds and labels for each point in a point cloud, our goal is to find a segmentation model such that the difference between the prediction model and the label ground truth is almost minimized. How do we represent the point clouds? Similar to PolarNet model, we use our polar bird eye view representation. The use of Polar bird eye view representation is of twofold advantages. It evenly distributes the points. More balanced point distributions will try to reduce the burden on predictors. How we will convert point cloud to pseudo bird eye view generation? Point cloud is discretized to evenly spaced grid in rho theta plane, creating a set of uniform sized voxels. Points in each voxels are then augmented with 9 features. On the augmented data, we use PointNet algorithm. After encoding, features are scattered back to the original voxel location to create a 2D pseudo image. On the pseudo bird eye view image, we can apply CNN backbone, which follows unit style of architecture consisting of top-down encoder and bottom-up decoder network. In encoder network, multi-scale voxelization data is added to the multi-scale features of the encoder. Hence, we construct rich hierarchical feature pyramid for multiple voxel features. Total downsampling factor of encoder is 16 with respect to pseudo bird eye view image. Bottom-up decoder does multi-scale feature aggregation. To enrich the feature maps of the encoder, we use Atros convolution. In this above equation, when r is equal to 1, it will be a standard convolution. When r is greater than 1, it will be a dilated convolution. ASPP uses 4 such parallel Atros convolution with different dilation rates to handle segmentation of object at different scales. Similar to ASPP, we use dense ASPP. It combines the advantages of parallel and cascade use of dilated convolution layers to produce more scale features over a wider range. By using these dense connections, not only a dense feature pyramid is included, but also larger receptive fields are embedded to perceive wider environment information. Most of the public datasets available are highly imbalanced, including Semantic kitty. In this Semantic kitty dataset, traffic sign, bicycle, motorcycle appear less in scene as compared to road, trucks, or car or pedestrian. This imbalance between the classes makes the network more biased towards dominant classes, hence poor semantic segmentation accuracy. To boost the accuracy of the underrepresented classes, we use weighted cross entropy loss function, and these weights are derived from taking the square root of the inverse class frequencies. Now we have a total loss function which is nothing but weighted cross entropy loss along with lowest softmax loss to do LIDAR semantic segmentation. Coming to the environment setup, we use Tesla K80 for training, Titan V GPU to do the inference with a batch size of 2, and we ran it for 50 epochs, and we follow the data augmentation similar to PolarNet model. Coming to semantic kitty validation dataset, we achieve 60.6 MIOU, whereas our baseline polar segmentation models achieves only 58.17 MIOU. On test dataset on leaderboard, we were able to get 60.01 MIOU, whereas polar segmentation model achieves 57.2 MIOU, thereby achieving our superiority in terms of accuracy. With respect to training time, our model takes very much lesser time to train with only 6 epochs to achieve a reasonable accuracy of 57.94, whereas polar segmentation model requires 23 epochs, which is too high. Coming to network performance and inference timing analysis, our high resolution grid model achieves 60.6 MIOU at 49 millisecond, whereas our low resolution grid model G3 achieves 54.12 MIOU at 29 millisecond. Coming to state-of-art performance and semantic kitty leaderboard, our model achieves 60.01, ranked at 19th position, whereas polar segmentation model achieves 57.2 MIOU and it was ranked at 34 at the time of submission. To improve, we will try to replace unit backbone with the state-of-art backbones, and we will try to make use of transformers to incorporate the attention mechanism. Currently, I am open for job opportunities anywhere. My mail